Okay, so today what I'd like to do is we'll talk about sedimentation. We'll go through an example here. I have put together a set of design specifications. So I've written this essentially as your colleague has done these calculations. You are asked then to check the calculations to make sure they meet all of the design criteria. So we have a maximum daily design flow of 0.2 cubic meters per second. It's about 4 mgd. We've got 5 tanks, a chain and flight sludge collector. Your colleague has calculated the tank to be 60 meters long, which is actually the maximum length for a chain and flight sludge collector. The width of the tank is 4 meters. The water depth of the tank is 2 meters. The depth of the sludge zone is 1 meter. Freeboard is 0.6. And there are 2 launders per tank, and each launder is 20 meters long. Okay, and they're 1 meter from the edge on the center. So what I want you to do, so the first thing I want you to do is just using the specifications, draw a plan and a profile view. So plan view looking down, profile view looking into the unit. So do the best you can. Talk about this, talk about the information that is given, and see what you can do in terms of a plan, of the plan and profile view. I know that that's a little bit difficult of a exercise to do online, but let's think about what you were asked to do. Okay, we have a tank, and typically it looks something essentially like this. So we have an influent pipe here, and we've said it's 40 meters long and 60 meters long and 4 meters wide. We have 2 what we call launders, and I'm not drawing this to scale. So the launders are basically a channel with weirs on either side. So in this case, we would have weirs on either side. The water flows into the launders and then is collected at a channel, the end here, and then piped onto the next process. And we have below this a set of chain and T rails. So basically, this is a mechanism by which the sludge can be pushed into the hopper so it can be pumped for further treatment. If we look at the profile view, now we're looking into the basin. So what we have here is, we'll draw it this way. We have a hopper here. Okay, so this is the sludge hopper. We have a pipe. Sludge can then be pumped from there for further treatment. We have an influent channel here, but at least this gives you a sense. We have an effluent channel here. We have what is referred to as freeboard. So this is 0.6 meters. And this is just space on the top of the water level to ensure that we don't have water flowing and splashing over the sides of the tank. We have a mechanism here. So this is our chain and flight mechanism. And this pushes sludge into the hopper. And actually, it should have been It's drawn this way so that there's a hopper. Okay. We have 2 meters of, this is our water depth, and we have 1 meter of sludge zone. So we're allowing 1 meter for that sludge to accumulate. And I apologize that I didn't draw this hopper quite well, very well there. Okay. And then on top of that, okay, we also have these launders. So this is our launder that is collecting water, and then that water flows into the effluent channel. So the chain and flight mechanism pushes the sludge that's settled into the sludge hopper. The sludge is pumped from that hopper to the next process for treatment. And as I mentioned, water's entering the effluent channel and then leaves on the opposite side in the enters in the influent channel and leaves in the effluent channel. So this is essentially a horizontal sedimentation basin. So the language that you should know are influent, effluent, freeboard, the water depth, the sludge zone, what a launder is, and what a weir is. Okay, the water flows over the weir into the launder and then into the effluent channel. What I would like you to do next in the breakout rooms, and what we're essentially going through, is some of the terminology. So I'd like you to talk over in the groups to determine the detention time and the overflow rate in this system. So we have Q is equal to 0.2 meters cubed per second. You're told that there's 4 tanks. And typically the detention time is given in hours. So we have 0.2 meters cubed per second times 3,600 seconds per hour. And that is equal to 720 meters cubed per hour. The volume is just the width times the length times, and we'll use the water depth. That is what we have in terms of depth for the sedimentation zone. So that is equal to 480 cubic meters. So the detention time is equal to the volume over the flow rate, and that is 480 meters cubed divided by 720 divided by 4 meters cubed per hour, and that is equal to 2.7 hours. In your design, and I'll be posting mini design 1 this week. In this design, according to the GLUM standards, which is the Great Lakes Upper Mississippi River Basin, also known as the 10 state standards, guideline that you'll use in all of your designs, says that the minimum of 4 hours is required unless V0, the overflow rate, is less than 1.2 meters per hour, which is equivalent to 28.8 meters per day. Notice that that's meters cubed per meter squared per day, which is meters per day. Okay. The overflow rate, some of you have gone ahead and gotten this. Okay, so the overflow rate is equal to Q over A sub S, or Q over the length times the width, which is also equal to the depth divided by T0. And that is equal to 17,280 meters cubed per day, using meters cubed per day because that's the conventional set of units, divided by 4, divided by 60 meters, times the width, 4 meters, which is equal to 18 meters cubed per meter squared per day, which is 18 meters per day. And if you divide 2.0 divided by 2.67, this 2.7 is actually 2.67 hours, and multiply by 24 hours per day, that is also equal to 18 meters per day. You should get the same answer irrespective. Okay. So your units may be different, but typically we'll use meters per day or meters cubed per meter squared per day. For overflow rates, we'll use hours for detention time. I know it's goofy, but this is the conventional set of units. Okay. The next thing that I'd like you to do is to determine the weir loading rate and the average horizontal fluid velocity. So the weir loading rate, typically the units here are meters cubed per meter per day, and that's meter length of weir. And we want this to be less than 250 meters cubed per meter per day. Okay, so our weir loading rate is 17,280 meters cubed per day. Divide that by 4 since we have 4 tanks. We'll divide that by 20 meters. It's the length of the weir. We have two launders, and we have 2 sides to each launder. Okay. In some cases, these are designed with only one side. We could have done, as you'll see, we could have only had weirs on one side. And that gives us 54 meters cubed per meter per day. That is well less than 250, so we're fine there. The next thing you're asked to do is to calculate the average horizontal fluid velocity. This is V sub F, and this is Q, and I'm going to use A sub X. This is the 0.2 meters cubed per second. Now this is typically in meters per second. We'll divide that by 4. And this is think of the cross section across which water is flowing. So we have 2 meters depth and 4 meters width. Okay, notice we never use the depth of the sledge zone, nor do we use the depth of the freeboard. And that is equal to 0.00625 meters per second. And the criteria that we're using, we want this between 0.005 to 0.018 meters per second. So that's the range that we need. Okay. It's fairly mechanical. The biggest challenge in your design is going to be to set the design constraints that they meet the criteria. And that's one of the biggest challenges. Okay, the last set of calculations, we'll do it for the Reynolds number. So the Reynolds number, we're looking at ensuring that we have laminar flow. And the Freund number, we're calculating to try and avoid back mixing. So to calculate the Reynolds number, so the Reynolds number is equal to the average horizontal fluid velocity times the hydraulic radius divided by the dynamic viscosity. So for sedimentation basins, that's what you will use. The hydraulic radius is equal to the area, and it's that area X, divided by the wetted perimeter. So this is 2 meters depth times 4 meters width, divided by 2 meters, which depth, plus the width, plus the depth. You're looking at the basin in this direction. So we have 2 meters, and 4 meters width. And that is equal to 1.0. We just calculated the average hydraulic velocity, and that is 0.00625 meters per second. Don't forget, you've got 4 tanks times 1.0 meter divided by the dynamic viscosity at 10 degrees C, and that is equal to 4,782. And you want this less than 20,000, according to the textbook. So we've met that criteria. The Freund number is used to assess whether or not we have back mixing. We want flow in one direction. We don't want back flow towards the influent. And this is equal to the average horizontal velocity squared divided by the gravitational acceleration times the hydraulic radius. And that is equal to 0.00625 meters per second squared divided by 9.81 meters per second squared times 1.0 meter, and that is 3.98 times 10 to the minus 6. We actually want this greater than 10 to the minus 5. We want it less than 1, but it'll never approach that. We have not met the criteria. But as you will find in the design calculations that it's very difficult to meet all of the design criteria. As long as you're close to this, we're going to say we're good. So my advice with all of this, learn how to use Solver on Excel. So setting up your Excel spreadsheet, setting up the criteria will greatly assist in your design for the design project.